Good morning, all. Today, we discuss one of the applications of operation amplifier, that is inverting amplifier. In the previous session, we discussed about the basics of operational amplifier. In that, I mentioned about its two inputs. One is inverting terminal and the other is non-inverting terminal. Mainly, an operation amplifier is used as inverting amplifier and non-inverting amplifier. Here we go to discuss more about the inverting amplifier. We have discussed open loop gain and closed loop gain in the case of an operational amplifier. We mentioned that when some fraction of output is fed back into input, the gain is known as closed loop voltage gain. Look at the figure. This is the inverting mode of operational amplifier. Here, an input signal Vin is applied through a input resistor Ri to the inverting input or the minus negative input. The output is fed back to the same minus input through a feedback resistor Rf. The plus input or the non-inverting input is grounded. The resistor Rf provides negative feedback because of we know that when input is given at the negative terminal or the inverting terminal, the output must be 180-degree out of phase. So the output and input must be 180 out of phase. So it must be negative feedback. Here the output is 180 out of phase compared to the input. Hence, we call it as an inverting amplifier. Next, we discuss an important term in the operation of operational amplifiers, that is virtual ground. We mentioned about the input impedance of an operation amplifier in the previous session. We know that the input impedance of operational amplifier is very high, or it is infinite. So there is no current at the inverting input. As the input impedance is very high, so the amplifier allow no current flows to it. If there is no current through the input impedance, then there must be no voltage drop. We know that the voltage drop is the product of current and resistance. As there is no current, the voltage drop between the inverting and non-inverting terminal must be 0. Look at the figure here. It is inverting terminal and it is non-inverting terminal. Here the input impedance is very high, so the voltage drop across these terminals, input terminals, must be 0. So in the non-inverting terminal, is grounded. Here the non-inverting terminal is grounded. That means here the potential must be equal to 0. So here the potential difference between the inverting terminal and non-inverting terminal also 0. Then at the point A also there is 0 potential. So we take the ground as 0 potential, but at the point A, it is not the actual ground. It is not connected to the ground, but at the point A, the potential is 0, so we call it as virtual ground. At the point A, it is virtual ground. The 0 volt at the inverting terminal, that is at the point A, that is referred to as virtual ground. The point A is said to be at virtual ground because it is at 0 volt. But it is not physically connected to the ground. Isn't it? It is not physically connected to the ground. So we call it as virtual ground. Next, we discuss the voltage gain of an inverting amplifier. Look at the figure. Here, in the figure, a input Vin is given at the inverting terminal through a resistor Ri, and In is the current passing through the resistor, and we know that at the point A it is at virtual ground. So the current flowing to the op amp is 0, and a feedback resistor is connected between output and the negative input terminal. It is RF, and we take that the current through the RF is IF. We know that the input impedance of this op amp is infinitely high, so the current I1 to the inverting input is 0. Therefore, the current I in that is flowing through the Ri, that entirely flows through the RF resistor. So we can say that the value of IF must be equal to IA. The current I in is completely flows through, the current I in completely flows through RF as IF. So the quantity IF must be equal to IA. Okay. So using this idea, we can obtain the connection between V out and V in. What do you mean by voltage gain of an amplifier? Voltage gain of an amplifier must be the ratio of output voltage to the input voltage. Okay. Voltage gain is the ratio of output voltage to the input voltage. Okay. So first we have to find the value of IN. Looking at the figure, IN is the current flowing through the resistor Ri. So the current, we know that current is equal to the voltage across Ri divided by Ri, isn't it? Then what will be the voltage potential drop across Ri? It must be equal to the difference between these quantity. That is V in minus VA. It is the voltage. V in minus VA. It is the potential difference across Ri divided by Ri. What is the value of VA? We know that the potential at the terminal A is 0 due to the virtual ground. So I in must be equal to V in divided by Ri. V in divided by Ri. And what is the value of IF? IF is the current flowing through the resistor RF. So it is equal to the voltage. It is equal to the voltage across RF divided by RF. It can be written as the voltage across RF must be equal to VA minus V out divided by RF. We know that VA is equal to 0. So IF is equal to minus V out divided by RF. So we get IN is equal to, I in is equal to V in divided by Ri, and IF is equal to minus V out divided by RF. We know that the current I in completely pass through the feedback resistor as IF. So we equate these two. That is V in divided by Ri must be equal to what? Must be equal to V out divided by RF. It is equal to minus V out divided by RF. IF is equal to minus V out divided by RF. From that, we can obtain the relation for V out, the ratio V out divided by V in must be equal to what? V out divided by V in must be equal to minus RF divided by minus RF divided by R in. What is V out divided by V in? It is the gain. It is the closed loop gain of inverting amplifier. So the inverting amplifier, the output, we know that the output is 180 out of phase. So V out divided by V in ratio gives a negative sign that give us the idea that the signal is out of phase with the output. So the gain of inverting amplifier is minus RF divided by RA. Okay. The negative sign of the gain indicates that the output signal is inverted as compared to the input signal. The closed loop voltage gain is independent of the op-amp internal open loop voltage gain. Why? We get the closed loop gain ACL is equal to, we get it as minus RF divided by RI. So it is independent of the open loop voltage gain. Thus the negative feedback stabilizes the voltage gain. The inverting amplifier can be designed for unity gain. We know that the expression for gain is minus RF divided by RI. That is the expression for gain. So if RF is equal to RI, if RF is equal to RI, gain must be equal to minus 1. Then it is unit gain. Therefore, such a circuit provides unity voltage gain with 180 phase inversion. And if RF is some multiple of RI, the amplifier gain must be a constant. For example, if RF is equal to 10R, if RF is equal to 10R, the gain must be equal to minus 10. So such an amplifier gives an voltage gain exactly 10 along with a 180 phase inversion. If we select a precise resistor values for RF and RI, we can obtain a wide range of voltage gain. That is, using the same operational amplifier, we can obtain different voltage gain as we require. Next, the input and output impedance of inverting amplifier. First, we discuss about the input impedance. We know that an operational amplifier has extremely high input impedance. Here we discuss the inverting amplifier. The inverting amplifier does not have such an extremely high input impedance. Input impedance of this amplifier can be found out from the given figure. Here, this point, we will give our input voltage. Okay. We know that at this point, let it be A. At this point, there must be a virtual ground. So, our source, input source, see a resistor Ri at the input terminal. Thus, the input impedance of the inverting amplifier is Zi must be equal to Ri. I draw a simple figure here. That is, if it is our source, it gives an input, okay, and this is our Ri. Here at the end of this Ri, it is at virtual ground. So the potential is 0. So our source see this as the input impedance. So Zi must be this one. Okay. Now we go to the output impedance. From the figure, the output impedance of the inverting amplifier can be seen as, it must be the parallel combination of RF and the output impedance of the op-amp. Here at this point there is a virtual ground, but it is the Z out of the inverting amplifier. Here it is the Z out of the inverting amplifier and it is of op-amp. Then this RF can be treated as, it is at virtual point, then this point can be taken as it is virtual ground. We can't represent it as ground, it is virtual ground. Then this RF and the output of the op-amp, output of this op-amp in parallel combination offer the output impedance of the inverting amplifier. So we conclude this session here. We will discuss the non-inverting amplifier in the next session. Thank you.